welcome to Studying with Chris, where I try my best to explain topics to help both you and me understand. Today, I was just struggling with another physics problem, so let's give it a shot. So this is another version of a half-Atwood problem, if you'd like to pause the video and give it a shot. Otherwise, I'll start now. So in this case, we're given masses 1 and 2, and we're looking for the acceleration of the system. And since the acceleration is within the system, it's the same for both mass 1 and mass 2, so it doesn't really matter for which one we find. So we're also going to assume in this case that the surface is frictionless, so we don't have to account for friction. Let's start by drawing our free body diagrams. So over here on mass 1, let's write, since it's frictionless, the only force is from the string, so we can say the only force is this way from force tension. Now over here on mass 2, we have force tension pulling it up and force of gravity pulling it down. So we can write that for, we'll just label it mass 1. And for mass 2, we have force tension and force of gravity. Now, next to it, we can write that the F net for mass 1, F net is equal to Ft. And over here, we can write that F net, and since we know it's heading downwards, we can say that we know that Fg is greater than Ft. So we can say that F net is equal to force of gravity minus force of tension. Now we know that F net can also be written as mass times acceleration from Newton's second law. So we can write this as mass times acceleration equals to Ft, and mass times acceleration is equal to force of gravity minus force tension. Now we're looking for acceleration. I'm not really interested about force tension, so what I'm going to do is I'm going to make force tension the common equal to, if that makes sense. So I'm going to try to isolate Ft so I can make the two equations equal to each other and make a system of equations. So what's that going to look like? So over here we're just going to isolate force tension, which means I'm going to add force tension and subtract F net. So this ends up looking like Ft is equal to Fg minus M2a. Now since we have M1a is equal to Ft, and since we know the force tensions aren't changing because it's the same string, we can rewrite this as M1a is equal to, I'm also going to rewrite this Fg really quickly, to M2g minus M2a. Now, for force of gravity, the reason I'm using M2 only and not M1 is because the only force of gravity that we really need to worry about right now is from M2. M1 isn't affecting the force of gravity of M2, so we only need to use mass 2 times g. And we can see here that we have an A and A, so let's substitute our variables really quickly just to see what it looks like. So we know that mass 1 is 3.4 kilograms, so we can say that 3.4a is equal to mass 2, which is 1.5 g minus 1.5a. Now let's bring both of these a's to the other side. So we have 1.5a plus 1.5a, and we'll get 4.9. So 4.9a is equal to 1.5g. And we know g is just 9.81, so we can do that really quickly. And we'll get 14.715 is equal to 4.9a. Let's divide by 4.9 to isolate for a. And we'll get that a is equal to approximately three, let's put it to one sig dig, or sorry, two sig digs, 3.0 meters per second squared. Awesome. So overall, not too tricky, just takes some thinking. I was just struggled with this question a little, so I just want to try it out and try explaining it in my own words. If you have any questions, please let me know. Otherwise, thank you for studying with me.